everyone. I hope you're having a wonderful day. My name is Kyle Collins, and I will be taking you to the fifth Physics 2212 lab, Magnetic Braking with Faraday. In this video, I will go through the purpose of the lab, explain essentials, show you the preview, then show you our data, show you the glow script code and computational model, and then answer questions to conclude. The purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet/tube interaction, compare the computational predictions with the observed data. So essentials formulas we are going to need is Faraday's law, Lenz's law, Biot-Savart law, Newton's second and third laws, and time derivative of magnetic flux. Also, we will need Ohm's law and loop magnetic force. Here are the preview of our results. So our experimental time is 1.13 seconds, and our computational time is 1.088 seconds, which is, I would say, pretty close. And here it's the magnet going down the tube. So here's our data. The length of the tube was 0.7 meters. Width of the foil was 0.003 meters. Radius of the tube was 0.0135 meters. Magnetic dipole was 2.84 from lab 3. Mass of the magnet was 0.24 kilograms. Mu was 2.84. And our average time was 1.13. So here are the trials. So our first trial was 1.1 seconds. Second trial was 1.09 seconds. So on, and we got 1.13 as our average. So here are some checkpoint questions. Why can't we use a Faraday tube? So a Faraday tube contains iron, which will interfere with the magnet, causing incorrect results, making our data not correct. And what happens to a magnet? How does it compare to a magnet falling in free space with no tube? It'll be falling slower, so we will get different results. So here is our glow script code. We plugged in our initials. Then we had to use the dipole formula, which is mu over 4 pi epsilon naught 1 over r cubed, and times our b, which was from our lab 3. And we calculated the flux using the flux equation.
Simulation loop, which calculates
And here we made our simulation.
the force on the magnet from the loop and the force due to gravity to find the net force. The loop also updates.
Here is our loop. So it tells us where the magnet is and the force when it's going down throughout the tube. Here we had to calculate the magnetic force and change the line of force on the magnet. What do we know? Our estimate is pretty close to the experiment, and with that we can say that the results from lab 3 may be inaccurate because of our AM squared was we had 2.84 our mu, but other than that, and possible sources of error, every lab has some type of error, not accurately recording the time of the fall, contact between the magnet and tube, air resistance, inaccurate measure of dimensions, consistency, all types of stuff could have messed up the. So questions: what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the following magnet change? It would be near zero resistance, which would lead to a larger induced current, giving a larger magnetic force. The dynamics would change because of Newton's third law, which would make the magnet fall slower. What if holes or slots were cut into the tube? How would this affect the ring's current in the model? It would reduce the induced current basically by doing the opposite of what the top question asks. This would make the magnet fall faster. Thank you for watching. I hope you enjoyed.